All right, in this video, we're going to take a look at a type of passive transport called osmosis. The way you know something in a problem is related to osmosis is if you get a scenario where water is moving or a cell is getting larger or smaller, because volumes of cells can change when water move. All right, so the most important thing to keep in mind is the direction that water moves. So add this to your notes. Water always moves to the side with higher, I'm going to use a different word here. I'm going to use more, because sometimes when I write higher, students think like geographically higher on the paper or something like that. But the side with more solute concentration. Okay, and solute here refers to things that are dissolved in water, like salt and sugar. All right, so we're going to take a look at a couple scenarios. All right, first one is that's a pretty shriveled up cell. That's kind of extreme. But anyway, what would cause a cell to shrivel up? Well, a cell will shrivel up is water is leaving the cell. Okay, so we're going to draw the dots here to represent the solute. Water would leave a cell if the solution or the environment outside the cell has more solute than inside the cell. All right, so this kind of solution is known as a hypertonic solution. All right, hyper means more, so the solution has more solute. Okay. Let me draw this a little bigger. All right, so you have an oval-shaped cell, and this one is a normal-looking cell, and that's because water is entering and leaving the cell at the same rate. All right, so the reason that would happen is because there's equal concentrations of solute in and out of the cell. All right, there's about the same amount in and out, and so that's known as an isotonic solution. Iso meaning equal or 1-to-1. All right, so we're referring to the environment here, not the cell. Okay, in our final example, we have a swollen cell, so kind of like a circular cell. So what way do you think water moves for a cell to swell? Well, water would enter the cell for a cell to swell up like that. Okay, so go ahead. If you can see the pattern, which side of the cell has a higher concentration of solute or more solute? All right, hopefully you see the pattern here. Water goes to the side, there's more solute. Generally, there's not going to be like a different amount of solute in the cell, but there'll be much less solute outside the cell. So that's the thing here. That's the takeaway. So that's known as a hypotonic solution. Hypo means below, or there's less solute outside the cell. All right, so these are the three types of cells that you want to get familiar with. Now, there's also commonly on tests these things called U-tubes. So get back to they're just U-shaped tubes. Okay, and they're separated by a semi-permeable membrane. What that means is water can pass through, but solute cannot. All right, what you'll have is like water filled up in this tube, and you'll have on one side you'll often have more solute than the other side, or a higher concentration. So given time, over time, what do you think that U-tube would look like? Which way do you expect, would you expect the water to go? Well, because there's more solute on the left side, that's the direction water is going to go. So on the right side, the water level will decrease. On the left side, the water level will increase. And again, all of that, 1, 2, 3, 4, 5, 6, try to make this equal, is to try to equalize the concentration of solute. I'll draw the other scenario here. There's my semi-permeable membrane. Get about equal level of water. And here, let's say there's more solute. I'll draw 6 dots there on the right side. Okay, well, given time, that water is going to go to the right side because that's where there's more solute. So you would expect the right side to have more water over time than the left side because the solute can't move through the membrane, the water does. Okay, so it's more equal in the after scenario. We call that equilibrium. All right, passive transport doesn't use energy and it moves things until equilibrium is reached.